Next, let's see exercise 8. This is part A. There is a part B also. Two integers a and n are given, where n of course is positive. A may be negative also. It is given that a is relatively prime to n. Their GCD is 1. Then we have to prove that a solution of this linear congruence, ax congruent to b modulo n, is this: x congruent to b times a to the power phi of n minus 1 mod n. B of course is some integer. The solution is almost trivial. So a and n are relatively prime and you know what to do next. Because of this condition, Euler's theorem immediately gives you this congruence. A to the power phi of n is congruent to 1 modulo n. Now all we do is we use this proposed value in this congruence. We just calculate ax with this in place of x and see what it becomes congruent to modulo n. So that is a times this, which is of course congruent to and in fact actually equal to b times a to the power phi of n. This however is congruent to 1, so you get b times this congruent to b times 1, which is congruent to b modulo n. That's it. A times this is congruent to b modulo n. So this is a legitimate solution. Then in part B, we have to use part A to solve the following linear congruences. So we first considered this congruence, 3x congruent to 5 modulo 26. We straight away write what part A gives us. This should be the solution, x congruent to 5 times 3 to the power 5 of the modulus, phi value minus 1. So it turns out that this exponent is 11. Now all we have to do is we have to reduce this modulo 26. We split this 11th power of 3 like this. The cube of 3 cube, because if you multiply these two 3's, you are going to get 9. 9 plus 2 is 11. So 5 times 9 is 45, and what is 3 cube? 3 cube is 27, which is congruent to 1 modulo 26. So there you have a simplification. It becomes 1 cube. Becomes 1 cube means it's congruent to 1 cube. Okay. So this is congruent to 45 times 1 cube, and 45 is congruent to 19 modulo 26. So this is your answer. I want you to use this value here and see if it's really matching the congruence. Then we have this second one, 13x is congruent to 2 modulo 40. So again by part A, this should be the solution. 2 times 13 to the power phi of 40 minus 1. Phi of 40 minus 1 is 15. I want you to actually go through these calculations, okay? Don't just blindly write these things down. And then what we do, then we know what to do, because we will now have to reduce this entire thing modulo 40. So we first split this power of 13 like this. The 7th power of 13 square times 13, because 2 times 7 is 14, 14 plus 1 is 15. And then it turns out that 13 square is congruent to 9 modulo 40. So that's why we can replace this 13 square with 9. And 13 times 2 is 26. And then we have to again split this power of 9. And we do it like this. In place of the 7th power of 9, we write the cube of 9 square times 9, because 3 times 2 is 6, 6 plus 1 is 7. And here finally you have a simplification which you want. 9 square is what? 81, and 81 is congruent to 1 modulo 40, because 80 is divisible by 40, 81 minus 1. And 9 times 26 is 234. So then you go through a simple calculation. You divide 234 by 40 and the remainder is 34. So this is your answer, reduced modulo 40. Here also you put this value here and see if the congruence is satisfied. And finally this third one, 10x is congruent to 21 modulo 49. So the solution is this, 21 times 10 to the power phi of 49 minus 1. This exponent is 41. Okay. So we split this power of 10 like this. the 20th power of 10 square times 10, because that ultimately becomes 41, right? I mean 2 times 20 is 40 plus 1 is 41. And then we multiply 21 and 10, we get 210, and 10 square, it turns out, is congruent to 2 modulo 49, which is a simple thing to verify. So here you replace the 100 by 2, and then you further split this power of 2 like this. 8 times 2 is 16 plus 4 is 20. So here you have 16 and here you have 14, you multiply these two, you get 224 times the 8th power of 2, it turns out, is congruent to 11 modulo 49. So here you can write 11. So that's how we are gradually simplifying things. And then this rest is just simple multiplication and reducing modulo 49 again and again. Eventually you get 7. So that is your answer. You do not fail to notice one thing, that although this method is instantly giving you a solution, but reducing the solution modulo that modulus itself becomes a computationally heavy thing. It nevertheless is a method for finding the solution. Next we have number 10, where we have two integers a and n. A is a positive integer and n is a non-negative integer. So n can be 0. That possibility is there. We have to show that these two integers, then a and this power of a, where the exponent is 4n plus 1, have the same last digit. And by now you know what that means. It means that we have to show that these two are congruent to each other modulo 10. And in that direction, we first make this simple observation. Note that these two integers, a and a to the power 4n plus 1, are either both even or both odd. They are both even when a is even. Otherwise, they are both odd. So that is why they are congruent to each other modulo 2. What is the reason? The reason is that when do we say that this is congruent to this modulo 2? When 2 divides this minus this. Now a difference of two even integers is even, it's divisible by 2, and a difference of two odd integers is also even. That is why we are having this congruence. And do you see why we have written this separately? Because we want modulus 10. But now we have 2, so next we are going to go for 5. And in the 5 case, there are two subcases. This is the first one, where 5 divides a. The other one is where 5 does not divide a. If 5 divides a, then of course this is congruent to a modulo 5, because both are divisible by 5, so their difference is also divisible by 5. And if 5 does not divide a, then we can apply Fermat's theorem here, obtaining this congruence. Note that 5 is a prime. That's why we are able to write this. A to the power 5 minus 1, that is 4, is congruent to 1 modulo 5. And so we can split this power of a like this, conveniently having the fourth power of a separately, and in its place you can write 1 because of this congruence, which comes from Fermat's theorem. And that's how you are having the fact again, this fact here as well in this subcase. So you now have these two congruences, that this is congruent to a modulo 2 and that same thing is also congruent to a modulo 5. And then you note that the two moduli are relatively prime. 2 and 5 have GCD 1. That's why you can combine those two moduli to have this modulus, composite modulus 10, and this congruence. And so a to the power 4n plus 1 and a have the same last digit. Let's see another one, number 12, where it's given that n is a positive integer and a definition is given of a set. We consider a set of this many integers, okay, phi of n. These integers are not necessarily positive, they can have any sign, but they are all relatively prime to n and they are incongruent modulo n. This means that if you choose any two distinct integers from this set of integers, they are not congruent to each other modulo n. They are mutually incongruent to one another modulo n. If so, then such a set is called a reduced set of residues modulo n. Then we have to verify some things. There are three parts. This is part A. These following integers form a reduced set of residues modulo 9. Let's see what the integers are. So you can see that some of these are negative. Minus 31, minus 16, minus 8, 13, 25 and 18. Now in the solution one can of course follow just the definition. One shows that each of these given integers is relatively prime to the modulus 9 and no two of them which are distinct are congruent to each other modulo 9. That however will become somewhat big, because even if you manage to show that these are all relatively prime to 9, but picking two distinct elements from this list and then seeing that they are not congruent, you will have to see a lot of incongruences. Instead, we do something else that will give us the solution more quickly. We note this. The positive integers less than 9 which are also relatively prime to 9 are these, which you already know: 1, 2, 4, 5, 7 and 8. And now you note these congruences. You take each of the given numbers in the list and see to what number it is congruent to modulo 9. You will see that those numbers, that is, you take the numbers, these numbers are in the list, right, in the given list, you reduce each one of them modulo 9. You find that they reduce to just these numbers: minus 31 to 5, minus 16 to 2, minus 8 to 1, 13 to 4, 25 to 7 and 80 to 8. And these are just these numbers in some order: 1, 2, 4, 5, 7, 8. 1, 2, 4, 5, 7, 8. Okay. But what do these congruences achieve? They do two things simultaneously. First of all, they show that these numbers which form that list of given numbers, these numbers are all relatively prime to 9. Why? That is because these numbers are relatively prime to 9. So from properties of congruences we know that these are also relatively prime to 9. Okay, that is one half of the definition of a reduced set of residues. And these same congruences also show that no two of these numbers can be congruent to each other modulo 9. How? Suppose that's not true. Say minus 16 is congruent to minus 8 modulo 9. Then 2 has to be congruent to 1 modulo 9, which you can verify numerically that it's not the case. However, you can be more clever and immediately see that no two of these numbers are congruent to each other modulo 9. And what is the reason? That is because they are all positive integers and they are less than 9. So their difference cannot possibly be divisible by 9. You see, because these numbers are less than 9, so you pick any two of them which are different and consider their difference. Say you pick 2 and 4, either you consider 2 minus 4 or 4 minus 2, that does not matter. Is it possible for 9 to divide 2 minus 4? No, because 2 minus 4 lies strictly between minus 9 and 9. And between these two bounds, if you remove these numbers also, minus 9 and 9, the only number that is divisible by 9 is 0. But if you pick different numbers from here, their difference is never 0. That is why these same congruences show that these given numbers are mutually incongruent modulo 9, and that is why they form a reduced set of residues modulo 9. So you did not have to pick two of them and see whether they are incongruent. Don't have to do those things. You just follow this procedure and you are done. And similar questions parts B and C. Only the lists and moduli are different. So in part B, you see the first 6 powers of 3 with positive integer exponents, and the modulus is 14. You have to show that these numbers form a reduced set of residues modulo 14, following an exactly similar procedure. And this is part C. The first 18 powers of 2 with positive integer exponents, and the modulus is 27. I leave these two parts to you because this is just a computation. There is no twist or anything in them.